Today we are going to continue looking at the displacement method, which we've been spending the last few lectures looking at. Today I'm going to introduce a new concept which will lead to a simplification of applying the displacement method, essentially because it eliminates a few degrees of freedom which you may need to consider otherwise. Okay. This one is involved. Remember that everything is essentially member force deformation relationships, and that's what I'm going to be looking at right now. So if you look at it, this is again displacement method, so just to lay the foundation. And the displacement method for the member force deformation relationship, this is our structure, right? And we say that the theta, then this is M AB theta AB, and then we have M BA theta BA, and there's also displacement BA. Remember last time, I'm just writing down the original slope deflection equations, and they come in this fashion. MAB is equal to 4 EI. EI is the constant flexural rigidity and L is the length, theta BA plus 2 EI by L theta BA minus 6 EI by L squared delta BA plus fixed end moment at AB, and MBA is equal to 2 EI by L theta AB plus 4 EI by L theta BA minus 6 EI upon L squared delta BA plus fixed end moment at BA. This is where theta AB and theta BA are the rotation of the tangent from the original tangent. Okay, remember that from the original undisplaced tangent to the displaced tangent are the definitions, and delta BA is the deflection of B. This is A, this is B. Deflection of B relative to A, upwards of B relative to A. Okay, and theta AB and theta BA are positive anticlockwise, and fixed end moment and moments are positive anticlockwise. Okay, so this is the original definition, and then in the last two lectures I introduced you to the concept of MAB is equal to 4 EI upon L theta AB plus 2 EI upon L theta BA plus fixed end moment at AB. MBA is equal to 2 EI theta AB plus 4 EI by L theta BA plus fixed end moment at BA. Okay. Now, if you look at this here, what are the definitions of theta AB and theta BA? These here are defined from the chord to the displaced tangent. From the chord, this chord is the straight line joining A and B. That's the chord. Okay. From the chord to the displaced tangent, that is theta AB. So here this, maybe I'll call it theta this way, just to distinguish it from these, where these are from the chord. The fixed end moment here and here remain the same. Okay. So these are the two definitions that I have looked at, where it's essentially the fixed, where you have both MAB and MBA. Okay. Now today I am going to introduce to you a different member. See, this is based on fixed member, and this is the force deformation, force or member rotation display relationship for a fixed beam. Okay. Today I am going to introduce you to a different, a beam with different end conditions. This is the beam that I am going to introduce you to. This is EI upon L, and note over here that the difference between the original fixed beam and this fixed hinged, this is a hinge here, fixed hinge beam, is the fact that you do not have, you know that MBA is equal to 0. Note that theta BA is not equal to 0. Okay, rotation can occur. Rotation can occur, but MBA cannot be non-zero, because at a hinge, see, this is the end hinge, and at the end hinge you know that MBA is equal to 0. Okay, so today I am going to introduce a different concept, that how do we, and this is MAB theta AB. Note that over here what I have to understand is what happens, what is the additional, see, MBA has to be equal to 0. In other words, what does that mean? It means that MBA, which is equal to 2EI by L. I am still using from the chord, the definition of from the chord. So I am now going to write down theta BA plus fixed end moment at BA. Okay. Now, for now, let us is equal to 0. For now, let us assume that I'll come to the fixed end moment later on. Let us just say that this is 0. For now, let's say it's 0. It's normally not 0, but for now, let's call it as 0. Then what do you have? You have 2EI upon L theta AB plus 4EI upon L theta BA is equal to 0. So what does that mean? It means that theta BA prime is equal to minus, and you look at it, 2I upon L divided by 4EI upon L, so that's half, minus half theta prime AB. Do you acknowledge that? This is just by putting it equal to 0. I am assuming this fixed end moment equal to 0. Okay. So you see that theta BA is equal to minus half. So now I substitute. So therefore, if MBA has to be equal to 0, theta BA has to be equal to minus half of theta AB. So now let us see what happens to MAB. MAB, which is equal to 4EI upon L theta AB prime plus 2EI upon L theta BA prime plus fixed end moment at AB, which for now I am in other words, I am considering the situation where there is no member load. Okay, what is this equal to? Now here I substitute this here, so this becomes 4EI upon L theta AB prime plus 2EI by L, and this is equal to this. Okay, so if you look at this, this becomes equal to 3EI upon L theta AB prime. In other words, what happens is, if you look at it, MBA is equal to 0 and MAB is equal to 3EI upon L theta AB prime. In other words, the only relationship that we are left with in this particular situation, the force deformation relationship, is MAB is equal to 3EI upon L theta AB. Because MBA is equal to 0. Okay. What is theta BA equal to? Well, it doesn't really matter in this particular case, because remember that the only reason why we are finding out rotations and displacements are essentially to find out the moments. And what happens here is, since you know that the moment over here is 0, you really don't need to find out this at all. You don't need to find it out. Okay. However, if you are really interested in finding it out, okay, you can always find out that since this is equal to 0, you can always find out what theta AB is equal to from this formulation. Now, the whole point here, so that this is for a fixed hinged member, this is the member, this is the force deformation relationship. Okay, where this angle, if you look at it, is from the chord to the this thing. If you want to define it in the original, so this one becomes if theta is taken from the chord to the displaced tangent, okay, and if you want to define it in the original sense, then you can show, I'm not going into the details here, but you can exactly in the same way you can show that this is equal to, this is the original definition, so delta B. So here, this is from the original tangent to the displaced tangent. The rotation is the angle from the original tangent to the displaced tangent, and delta BA is the displacement upwards of B relative to A. Okay. So, so this is it. Now, what about the fixed end moment? Up till now, we've not considered the fixed end moment. Now, you see, the advantage of this is that I can consider the fixed end moment separately and add it, because it's after all superposition. So let's look at what happens. And to consider the fixed end moment, it's very easy. This is equal to this, where, note that for this we know the fixed end moments, so it's FEM given any loading, any loading, we know fixed end moment and we know BA. Okay, you know how to compute these also, I have shown it to you. So here we are saying that this, so this is here and this is the modified fixed end moment. Okay, so we can call it modified fixed end moment is equal to this plus What is the reason? Okay, look at this, that I'm saying that this is the original one which we know how to compute, and this plus this, where if you look at it, what I am doing is I am actually applying the negative of the fixed end moment. You will see that why am I applying this negative fixed end moment? Because this plus this will ensure that this becomes equal to 0. The moment there is no fixed end moment because there is no fixed end. Okay, and all I have to do is find out this, because then I know that fixed end moment, the modified fixed end moment, I'll call this the modified fixed end moment, is equal to FEM AB plus FEM plus AB. You see this? Okay, because principal superposition is valid. So all I have to do is find out, see I know this I know from before, all I have to do is find out what this is given this load. Okay, let's see. If I apply a load, let's go back to the original equation. Okay, if I apply a load here, right? Let me say that I'm applying a moment here. We need to find out what is the fixed end moment at this. If I can do that, I have solved my problem. Okay, so let us see what happens. Okay, if you look at this particular situation, what do you have? You have theta AB equal to 0 and theta BA is not equal to 0. Right? This is the condition. Okay. So now here what I am doing is I am finding out MAB. This is the only loading on the system. So MAB is equal to 4EI into theta AB, which is 0. So it's going to be just 2EI upon L theta BA. Do you agree to that? Okay. We don't know what theta BA is, but do you agree to this? And since there is no load, there cannot be any fixed end moment. And what is MBA equal to? MBA is equal to 2EI upon L into theta AB, which is 0, into plus 4EI upon L theta BA. And since there are no moments applied, this is equal to, this is just it, there is no fixed end moment. Okay. And what is MBA equal to? By definition we know that MBA is equal to M, which implies that theta BA is equal to ML upon 4EI. Now all I need to do is substitute that into this, and what do I get? 2EI upon L M 4EI, which if you notice is equal to M by 2. In other words, and what is this MAB? MAB is the fixed end moment since theta AB is equal to 0. That means if I apply a load M here, the fixed end moment is M by 2. I have derived it using the equations. Okay. And since fixed end moment is equal to A, now here since I am applying minus fixed end moment at BA, so what is this fixed end moment equal to? It's going to be equal to minus fixed end moment at BA upon 2. Okay. So what does that become? That makes it ultimately that the, let me put it here itself, that the fixed end moment modified at AB is equal to fixed end moment on AB due to the fixed condition minus fixed end moment at BA upon 2, where these are obtained using the fixed. We know this. How to obtain this we know. Okay. Now let us apply it to a particular equation and see whether we get it from first principles also. Okay. So I am going to consider taking an example of load P being applied at L by 2, okay, and what are the fixed end moments? Okay, we can derive them, but we already know what the fixed end moments are. These are equal to PL upon 8, PL upon 8, this way. Okay, so if I were to find out for this situation, load applied at the center, what is this fixed end moment equal to? For the modified beam, the fixed end moment is equal to, now PL by 8, because fixed end moment at AB, okay, minus fixed end moment. Now note that the fixed end moment here is negative because it's clockwise, minus PL upon 8 divided by 2. So if you look at this, this becomes PL upon 8 plus PL upon 16, and this becomes 3PL upon 16. So this is equal to 3PL upon 16 when this end is hinged, the fixed end moment. Okay. So now I can derive this from first principles. How will I derive it from first principles? Let's think back. I want to satisfy you that whatever we have done, we should be able to obtain it for this also from first principles. So let us see what happens when I apply first principles. How do I go from first principles? I consider this, apply the load here, and note now under this load what's going to happen is it's going to go like this, okay, and what I am saying is that this plus a moment applied here, okay, such that if this is theta AB, I'll get minus theta AB. Minus theta AB 0, minus theta AB 0, okay, is going to be equal to right, and if this is the case, then this is equal to the fixed end moment. We've already looked at this. The only difference between the original and this one is, note that since this is the only one fixed, see, note that we don't need to satisfy this theta BA 0, and this can be theta BA due to M. Nowhere does theta BA 0 plus theta BA due to the moment have to be equal to 0. No. Why? Because it's a hinge. Rotation can go anything. Only thing is we cannot apply a moment here, and I'm not applying a moment anywhere. Note that I'm only applying the moment here. So this, since this is a hinge, its moment is 0. This is a hinge, moment is 0. Since I'm not applying a moment, this plus this is not going to give me a moment here. And this plus this is not equal to 0 because there can be rotation. Rotation is allowed, it cannot take a moment. So you see the difference between the original one and this one. So let us see what happens here. Let us go through the steps. So let me apply the load. Okay, due to the load, bending moment PL by 4 and it is sagging. Now I need to find out what? I need to find out theta AB due to the loading. So how do I do that? Virtual force L is this. Okay. Virtual force, I need to find out this, so I apply a virtual force here. And I find out the moment diagram. The moment diagram looks like this. So this is my small m diagram, this is my capital, and since EI is a constant, this gives me directly the m by EI diagram, and this gives me the small m. So what is theta AB 0 equal to? Theta AB 0 is equal to the area under this curve, so half, because there are two areas, so I have to consider PL upon 4 EI into L by 2 by half length into base. Okay, that's the area of the triangle. And since this is this way, I am taking that as positive, this is going to be negative. The value at this point, at the centroid, you will see that the value is equal to minus the value at the centroid of this part. Okay, centroid is at 2/3 of L by 2. 2/3 of L by 2 is 1/3 L. So if you look at 1/3 L from this side, you will see the value is equal to, and negative, because if this I consider as positive, this is negative. Okay, so and plus, then I have to consider this part. So it's going to be PL upon 4 EI into L by 2 into 1 by multiplied by the centroid value at this point. If you look at the centroid, again 2/3 upon L by 2, that's 1/3. So the value at this point is equal to 1/3, and again negative, because if this is positive, this is negative. So if we look at this, this is equal to, we get PL squared upon 16 EI. This is identical. Remember, we had computed this earlier also. Okay, so this PL squared upon 16 EI still remains the same. Now, what I need to do is, I need to find out a moment which will give me minus theta AB. So what I need to find out is due to a moment here, what is the rotation here? How do I find that out? Well, you will see that since this, let's go through it. I mean, you will see that it comes out from the original equation that we have towards Deflection relationship, but I'll do it from first principles. Due to this moment, what is the moment diagram? The moment diagram looks like this, and this is equal to m, and since EI is a constant, this is m. So I'm drawing the m by EI diagram. So I want to find out this theta AB. So again, without much ado, I apply a moment here, and this is unit moment here, and this is going to be the small m diagram. Okay? I'm not writing them big because you know already. Okay? So here, so what is the theta AB due to the moment? You will put this 2, and what do you get? The area under this curve is ML upon 2EI, M upon EI into length, half of length. Okay? That is, and where is this? This is at 2/3 the distance. At that value it is. And note, since this is hugging, this is the same direction, so it's positive. So it becomes equal to ML upon 3EI theta. Which, if you look at it, is actually the same. I mean, we could have found this out easily, because MAB is equal to 3EI upon L theta AB. We know this. And you will see that exactly the same relationship you get from here too. Okay? So now, since we know the theta AB, and this has to be equal to, so for if M has to be the fixed end moment, then this plus this has to be equal to 0. So therefore, what we have is fixed end moment at AB becomes equal to 3EI upon L. Okay, note that this was minus. Okay, so you see what we are getting is that theta AB is equal to minus PL squared upon 6EI. Minus is obvious because this is clockwise. Minus means clockwise. And this plus this plus this is equal to 0, because that is what you have here. It has to be minus of theta AB 0. So therefore, if we put that in, what do we get? We get it equal to 3I upon L minus 3I upon L, because this goes on the other side, multiplied by minus of PL squared upon 16EI. So if you look at this, this becomes minus PL upon 16. Sorry, minus minus plus. What is that then? What is the fixed end moment? For a load applied at L by 2, the fixed end moment over here is positive 3PL by, which means anti-clockwise. We've already derived that earlier. So therefore, you see, essentially what happens is that this I've derived from first principles. So essentially, if you look at it, and if you look at this, we got exactly the same thing from here too. Okay? And since we had this from the same, therefore, now I can say for certainty that I can write down the fixed end moment for this modified beam by just taking the fixed and just subtracting BA by 2. I'll always do this. This is the uniform equation that I'm going to use because I know the fixed end moment for the fixed case. Okay? So now what I'm going to do is I'm going to see how this changes. So therefore, if you look at this, ultimately the equation for this turns out to be MAB is equal to 3EIL upon theta. Now this is where you take it from the chord plus, and here I'm going to write down the expression for the fixed case. These are the fixed end moments from the fixed case. And this is algebraic. Okay, so if the sign of BA is different from AB, it becomes positive. Okay, so this becomes my new equation. Now I'm going to use this to solve a problem that we had solved earlier. Okay, what was the problem? I'll make the problem statement for you. If you look at it, the problem statement is a problem that you've seen earlier. So I'm going to just put it down. I'm going to use this procedure to solve. This was the problem A, B, C. This is the problem that we looked at earlier. Now note that in this particular case, if you look at member BC, okay, member AB, at B you have continuous, okay, so there is going to be a moment here, so we cannot consider this in this. But if you look at BC, C is an end support. Okay, end support. So at an end support, what do we have? We have moment, we know that moment is equal to 0. Remember, we had applied that moment at C is equal to 0 as one of the equilibrium equations. So now, in this particular case, since I know that the moment is equal to 0 and I am not interested in knowing what the rotation over here is, what is the only degree of freedom that I have? Theta B. Because note that I am not interested in theta C, because I know that the moment over here is equal to 0. So I am going to use a modified, for the AB I am going to use the original element, and for BC I am going to use a modified element. Let's see what happens. So I am going to define this problem in a different way. Earlier what had we done? We had taken AB as fixed, BC as fixed, and we had defined theta B and theta C. Both of those equations in there. I mean, both of those unknown displacements. Here I am only going to consider one unknown displacement. And let's see how we can solve this problem. You see this advantage of this problem, automatically you see that now with only 1 degree of freedom, we only need one equation. Okay, so things will become much simpler if you put that in. Okay, and so now let us go back and revisit that problem. So what we are going to do is we are going to be considering AB as a fixed. Okay, so as far as AB is considered, we are going to say AB is equal to 4 EI upon L theta AB plus 2 EI by L. Note that since there are no displacements, I am not even writing down the delta, because the chord, or you can say take it from the chord, it doesn't matter, plus fixed end moment at AB, and MBA is equal to 2 EI upon L theta B plus 4 EI upon L theta AB, and this is theta BA plus fixed end moment BA. So for AB, this is what I do, and the fixed end moment comes from this 120 kilonewton force acting at 4 meters. Okay. For BC, I am going to consider it this way. B is fixed, but C is the end hinge. So whenever you have an end hinge, you know that the moment, bending moment at that point is equal to 0, and so I'm going to use this, and I have this loading. Okay, this is 50 kilonewton per meter. So I'm going to put it equal to MAB is equal to 3EI upon L theta AB plus, and here I'm going to put down that these fixed end moments are the ones I would consider if they were fixed minus fixed end moment at CB upon 2. So for AB I consider this, for BC I consider this. Okay. Now for theta B equal to 0, so let us go through the steps. For theta B equal to 0, what does the thing look like? Sorry, for theta B equal to 1. Note that that's the only degree of freedom. So this is going to become 1. So you're going to have a displacement pattern that looks like this, and then over here. And note that over here it doesn't have to go to 0 because this is a hinge. It can take any value. What is the value over there? Well, actually, if you notice that this one is MBC is equal to theta BC. Now note over here that since in this equation, okay, there is no theta CB, I don't really care what the rotation over here is 0. I mean what the rotation over here is. So if I put this, I get that for theta B equal to 1, theta AB is equal to 0, theta BA is equal to 1, and theta BC is equal to 1. Theta CB, I don't know and I don't care, okay, because theta CB is not going to get into my equations, force deformation relationships anyway. Okay, so once I have that, that means now I can put down the expressions. I get MAB, and theta AB is equal to 0, so I get 2EI upon L. Theta BA is equal to theta B, so this becomes theta B plus fixed end moment at AB. MBA is equal to 4EI upon L theta B plus fixed end moment at BA. These don't look any different from what we had originally. They look identical. Okay, the only difference here is in this equation. MBC is equal to 3EI, and theta BC is equal to theta B, so plus, and here I have fixed end moment at BC minus fixed end moment at CB upon 2. Now I need to find out AB and BC, and note that I have already done those earlier, so I am just going to show you that. Okay, we have already evaluated these. These were the fixed. So AB is equal to plus 172.8, fixed end moment at BA is equal to minus 115.2, and fixed end moment BC is equal to 416 and minus 416. So having done that, I can plug in those values directly. So therefore, what do I get? My fixed end moment AB is equal to plus 172.8 kilonewton meter. Fixed end moment at BA is equal to minus 115 by 2, and I need to evaluate fixed end moment BC minus fixed end moment CB by 2. So this is going to be equal to fixed end moment is 416.7, then I have plus minus, and then fixed end moment was minus, so it's minus 416 over 2. So this becomes (416) plus 208.3, which is equal to 625. Okay, so this becomes 625 kilonewton meter. Okay, so now if these are the fixed end moments that I have. I put them in. Now the thing is, once I have all of those, I have these relationships. I need to write down the equilibrium condition. Now, since there is only one, the equilibrium condition, okay, satisfy yourself, becomes MBA plus MBC is equal to 0. So if I put that in, what do I get? I get 4 EI theta B minus 115.2. This is MBA, and MBC is equal to 3 EI upon L theta B and plus 625. This is the fixed end moment, is equal to 0. So this becomes what? 7 EI upon L theta B is equal to 4 499.8, and so theta B becomes equal to minus 71.4 L upon EI. Okay, once I have my theta B, I substitute it into my equations and I get MAB is equal to you will see that MAB is equal to 27.2 kilonewton meter. MBA will be equal to minus 406 kilonewton meter, and MBC will be equal to plus 406, which is what you got in the last time. So just by substituting this, you will get those values. Now, and 10 is of course this thing, so you will get L is 10. So this is multiplied by 10. Okay. Now the beauty of this essentially becomes this, that note that just 1 degree of freedom, so the equations become much easier, and the major advantage of this becomes this, that I've already made a 2 degree of freedom into a single degree of freedom. Now you may say that, well, there was not too much of a difference between 2 degree of freedom and a single degree of freedom. Okay, but when you go into multi degrees of freedom and you can eliminate a few of these degrees of freedom, you will see that it becomes a big issue. Okay, so this simplification does nothing to the solution process. It still remains exactly the same. The only thing that happens is that you land up getting this thing, what you may call it, you'll end up getting a much better solution space. Okay, so that's all I have to say in this particular case. We will see that as we go along, we are going to get many problems, and ultimately, let me just not, by the way, let's go back to this. I have made one small mistake and I just want to correct that mistake, because you may find yourself that this becomes actually is 509.8, and so if you look at this, this becomes 719, 72, and you get 72.8 into, and that's this gives you this. So this basically becomes theta BA becomes minus 728 upon EI. Okay, but 728 you will see will give you this. I just made a mistake in putting it down over here. Okay, so satisfy yourself that this is going to happen. So now I am going to just state the basic concept that you have to work with, that right in the beginning you have to decide whether you want to use this or whether you want to use this. Now, if a member, if the joint, either joint of the member is continuous, in other words, there is some other member connected over here, then you always have to use this. Okay? You can use this only when the end, this end happens to be the end support of a structure. So this can only be used if there is an end support. Okay? You cannot use this if there is another member connected over here. You cannot. Because if it's another member, then the moment at this point is not equal to 0. Is that clear? So you can use this only if you have an end support. Okay? And this, otherwise you have to always use this and use the member force deformation relationships for this. And for this, I would just now today I've shown you how the force deformation relationship is different for this one. Okay? So I hope today's lecture has made it clear to you that even in the displacement method, you can actually bring in simplifications to enable you to reduce some of the equations, equilibrium equations, and degrees of freedom, and thereby reduce the equilibrium conditions that you need to specify, and essentially ultimately you reduce the number of algebraic equations that you need to solve for finding out the displacements and hence the member end forces. Okay, thank you very much. Bye.